Alright, so I want to give you everything all in one shot and just kind of throw it at you guys so you have something to work with, because I don't know how often I'm going to get back to this tutorial to do all the examples and everything. So this is going to be a crash course in how to program the BM71 with your microchip PIC without all the extra details and everything. So I will put all the links to all the software I've written, all the source code, the exe files, all the tools you see in this video are going to be in the description. You'll also have to get some tools directly for microchip, and I'm going to show you exactly what you got to do right now. So I'm going to show you where to get it and everything. I want to show you where to get it in case they change the actual link address or whatever. So we're going to start off with the first tool. Is we actually need the user interface UI configuration tool found here. This is on the microchipdeveloper.com webpage, and I just kind of Googled this, to be honest. I don't know exactly how to get here from the beginning, but I am in the Bluetooth low energy section under the BM BLE modules, under the BM71, under application examples, generic BLE demos, and stopwatch demo here. Now, I just want to point out that the stopwatch demo is old code, but it is what I use to reverse engineer this whole process so that I could get to this point. So if you want another example or you want to do it differently, you can also use this stopwatch demo, which is the official microchip version. However, I found it super complicated, and it took me quite a while to kind of figure out what they were doing. So let me go ahead, and we're going to start off by downloading this tool here. It's under, you scroll down a little bit, and it's under the software tools. So I'm just going to save this, and I've already downloaded it, but I'm just going to save it again. Okay. Now the next thing I'm going to do here is we have 3 tools. Okay. Now again, I'll provide all the source code for this also in the links below. But these are the files I'm going to provide for you. So this IS187.102 BLEDK03 blah blah blah. This is the file we just downloaded. This is microchip's configurator for the BL71. So we're going to go ahead and extract this first. So I'm just going to extract it. Okay. Now, this next tool is BLEK3 Text2C. This is the code I wrote, and yes, again, I know it's probably written horribly, but it is written in C#. This is the executable version. So you extract this, and you've got the actual program. This is not actually the source code, although I will provide that. All right, the other tool I have, or the other file that I'm providing, is the actual firmware for the PIC 16F 18877. Now, you probably don't have this PIC. I understand that. However, I'm going to extract this. If you go into this project here, again, this is the project folder, the BM PIC project here. If you go into this and you go into BM71 for PIC, blah, 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 the rest of this is all just files that MPLAB X generates. But if you go to this custom files folder, this is my library for the BM71. I'm not a professional library writer or anything to that extent. I've just written a lot of embedded systems before. It's my hobby. I like doing it. I'm not, extremely proficient, whatever. So try not to rip me apart too much on this code, okay? All right. Now, this Bluetooth app command C, this is something I just started working on. This is the part of the code where I'm at, where I can actually start sending the XXAA commands, all right? So this is not fully developed, these app files. They're just something I'm starting to work on. However, this is the meat, the bread and butter of what I want to give you guys is the Bluetooth flash commands and the Bluetooth flash data. So you can, if you don't have this chip, you can just come in here and look at, and this is Notepad++, by the way, great program for viewing raw code. You can come in here and you can see I commented the crap out of everything, almost to a fault. I mean, there's just so much. I tried to explain every little step as I was going, why I was calculating things. So this is a lot more, I feel, intuitive and a lot better explained than the other code that Microchip gives you. Microchip gives you code that literally has like a few words. It's like, this command opens memory, and that is like all they tell you. So this hopefully will explain a lot more, and again, I'm sure that there's way more efficient ways to write this, and you guys are welcome to write it better, whatever. This is my attempt at it, okay? So the C file is all the actual commands that you need to run. The header obviously has all your definitions, and I have no idea why my headers want to open up in Visual Studio, but sure, whatever. And again, this is not properly formatted or anything. They're just kind of all thrown in there for the sake of getting it done. Now, this data file, okay, this is important. This is the custom file that I have that will automatically be generated by the program, okay? So this is where you just literally copy and paste the code that my program generates, and we'll get to that. Okay, so if you don't have this chip, you can just look at these files, the raw files, and get a really good idea on what's actually going on that way, okay? But I'm going to open this project up in MPLAB-X because I do have the chip, and I wanted you guys to be able to see it in action for one. Okay. So let's see. Here are my source files. Okay. Here's the custom files folder. These are all MCC generated files. So this is that. What is it? MPLAB code configurator version 3. While I have the ability to go through and configure the chips manually, it's just so much easier to use this add-on. If you haven't experienced this, haven't found this, it's not this Harmony generator thing. Forget this thing. It's this MPLAB code configurator version 3. If you haven't used that yet, I suggest you download it. It's an add-on inside of the MPLAB-X, so you can actually just go to Tools and Plugins download. Anyways, when you open it up, this is what it looks like if you're not familiar with it. So here it shows you your microchip. It shows you all the different functionality of your microchip. If you want to use something like a timer here, you can pick which timer. You double click on it, it'll add it to the project. You can easily I mean, it's just amazing. It just makes setting up the chip so much better. Are you sure you want to remove this? Yes. Now, you're going to see in my project, I have a timer here, timer 6. I didn't do this to throw you guys off. This timer 6 is not used anywhere in the project. It was just, it was something I planned on implementing in the future, which is where it would check after a certain amount of time to make sure that the BM71 responded. This is not implemented at all. Do not worry about this timer, even if you see it in the code. It's initialized in the code, but it's never actually utilized. However, the UART is a must. This is how we're going to communicate with the chip. So the UART needs to be at 115.2 K baud rate, and you want to get this error as low as possible. This error is based on your baud rate and the frequency of your chip, which is listed somewhere here. Anyways, you'll figure this out. You play around with this a little bit, and you will find there, it does list your actual, you can change the speed of the chip somewhere here. Anyways, oh, right here, system module. You can select the chip and the speed and all that. Okay, so anyways, this is a great tool, highly recommended. I want to talk about the pins a little bit before we get going too much here. So this is my pin configuration for the PIC 16F18877. Boy, I hope that is the number that I told you guys, because I think I said something else, but this is actually the chip I'm using. So here are basically the pin layouts for the BM71. I have my TX, my RX. Now, just if you're kind of wondering, the TX of the BM71, the TX for transmit, will go to the RX of the microchip, the receive. And the same for the TX of the microchip will go to the RX of the Bluetooth device. So make sure not to match them. They should not be matched with the BM71. They should be the opposite. Now here is the wake up GPIO I told you guys about. Now I have set it to this pin 44, but unfortunately, because again, as I mentioned before, I designed the circuit board before I realized I needed that wake up pin. So in reality, my wake up pin I cut into the RTS wire here, and this is actually the wake up pin, or the TX indicator pin on the Bluetooth module. I bring this up because if you do look at the C files, that's Bluetooth app commands, you will see one of the commands where I send the RTS pin low, and then I put it high again for 3 milliseconds, as I talked about in the other video. That pin really should be this wake up pin. It's because of my circuit board. I had to kind of splice and do what I could to get that to work. So just so that's not confusing. Now you do need the reset pin. I highly recommend putting the reset pin directly to your MCU, and do not put it to a push button, because every time you want to change something, you have to push that button. It'll get really frustrating. The CTS pin is not required on the initial programming. Really, I don't think it's required at all. Really, if you want to use it, you can use it. I only added it because when I first started this, I wasn't sure if the chip had CTS and RTS enabled by default. I found out afterwards it wasn't, but I added them just in case. The link drop pin I found not too important. Now, this might become important later as I work with the app commands, but so far I haven't found a need for it as far as flashing the firmware goes. Now, the status 1 and status 2, while they are not, they are useful, let me tell you that. So you can probe them, or you can check them by sending them to LEDs, the status of the LEDs. The status 1 and status 2 from the BM71 basically tells you what mode the BM71 is in. Now, when I say that, I don't mean it tells you whether you're in test mode or in application mode. What it does is each one of those modes has kind of different settings. So they have like a standby mode, an idle mode, a sleep mode, all these other different modes. And by pulling these two pins, it'll tell you what mode the BM71 is in, whether you're in application mode or test mode. Now, the sysconfig on the BM71 is an absolute must. You do have to have this pin connected. It allows you to change between application mode and test mode, and the test mode is what you will need to be able to enter to program or change the settings on the chip. So you have to have this. Okay, so I'm kind of going on a little bit too much, but this is the configuration of my chip. I've labeled each one of the pins. So if you come back to this video, if you see that I used LED1 or status 2 check, or syscon, if you see syscon particularly, if you see me put syscon high or something, it's this RC0 pin, so you can relate it. Okay, enough about the configurator. I think you can at least pause this video and see how my setup is if you run into any problems. And then, again, if you're new to the configurator, once you have everything selected the way you want, you click Generate Code, and it will populate all the files for you with the code to configure your chip the way you need it. Okay, let's talk about, let me close this MC stuff. All right, let's talk about the way the code works. So if we go to our main command, you can pretty much ignore all this stuff. This is just, I wanted a second delay instead of milliseconds, blah, blah, blah. You'll see that really there's only one command in the main code that actually programs the chip. This is where it all starts. It's check and update flash, okay? I'm going to go through basically really quick how this works. I'm not going to go into too much detail. It's all pretty much explained in the documentation anyways, but give you a general idea of what's going on here. So you first need to reset the chip to put it into test mode. Now, if you go into this, this may be a little bit confusing, basically because this BT reset is used both. BT reset basically just pulls down the reset pin and pulls it up. That's all this does, okay? But you need to put the syscon either low or high, the syscon pin, depending on whether you want to go into test mode or app mode. So I basically set the testcon pin high or low, depending on the mode I want to go into, and then I pulse the reset pin to restart the chip. Now, for the firmware, to change the settings, you want the app mode. No, I apologize. You want the test mode. Everything you're going to do for the flash is going to be in the test mode. The app mode is when you're done setting everything up, all the configuration. That's when you'll use the app mode. Okay? So let's go back to main. Go back. So that's what I'm doing here. I'm basically just resetting the chip and putting it in the test mode. Now, the first thing you have to do is you have to send the open flash memory command. Now, if you look at the top of this file, I have all of these commands labeled: open flash memory, read command, erase all flash, blah, blah, blah. You'll see that each one has a transmit and a response. Excuse me. The transmit command is the command you need to send first. Is the command you need to send to actually perform that task. The response command is what the unit should respond with. Okay. Now, there are some exceptions. There are some things, particularly with read command and write command, will actually use 147 bytes, even though it only says 19 here. We'll get into that a little bit in a minute. But these are all the commands that you will use to flash the firmware. This is what you're writing to the chip. These are not the AA commands that they list in the PDF. This is not the 0xAA commands. These are specific commands for test mode that allow you to perform these functions. Now, I have no idea exactly what these code... I couldn't tell you what this 0 or this 1 is. There's no clear documentation that I can find that explains exactly what this command does. I do know that it is the right command and that it should respond this way, basically from reverse engineering that other code, which I think I've talked about earlier. That's how I know where these commands come from and that they are right. Also, I know that they're right because I do get the chip respond with this exact command. So, that being said, these are where those commands are coming from. They're coming from the other code I was looking at. Couldn't tell you exactly what they do. I have general ideas, but I don't have anything specific. So you're just going to have to take my word for it that these do work. All right, so now let's go back to here. So the open flash memory basically is this open command, or this open flash memory. The chip won't let you do anything with its flash until you send this command. This basically is the start command. Nothing fancy to it. You just send these 17 bytes. It will respond with these 21 bytes to let you know that, yes, you've entered the flash mode. Okay, so that's what's going on here. Now, the FBT check config. This command hopefully is not too confusing. Essentially what it is doing is it is going through block by every 128 bytes, is going through, it first goes through the BM71's memory every 128 bytes of blocks of code. It is checking and it is comparing it to let me go to my header files. It is comparing it to this Bluetooth flash data here. Now, there's a few things about this. A few things I want to touch on. The reason why it does this is because it first wants to see, is the BM71 correctly configured now? Does it need to be reflashed? The flash memory on the BM71 does have a finite amount of writes to it. It's something like 100,000. It's probably something I'll never use, but if you're planning on using this product daily or all the time and you constantly reset the PIC or it's turned on and off and you're constantly writing to that flash memory, you will eventually wear out the BM71. It will no longer be able to retain the values you send it. To avoid this, we first go to the, sorry, I have to keep going back through the process of going back here. So to avoid this, we first read all the memory. Then we check, does it match the memory we want to send it, okay? If it doesn't match the configuration we want to send it, if it doesn't match, then we go through and we erase all the memory in the BM71. I'll get into why we erase all the memory first in a little bit. And then we go through and perform this command, which actually goes through and rewrites the memory on the BM71 the way we want it. Then we do another check here, check the config. It's the same command. It goes through and just confirms that the chip was in fact programmed and that all the data does match. And I just have, all I do is I have a LED turn on if we go into this mode and everything matches. Now you can do whatever you want here to confirm whether it matches or not. You can have an LCD display, whatever. That's what's going on here. So it only writes to the firmware if the firmware doesn't match what you want it to initially. Then we use the exit the flash memory code, which is, again here, close command, just like the open command, no surprise there, is just the close flash memory so that you can reset it and go into the application mode. Now the application mode is actually where you connect to devices and stuff, and that's where you'll be doing most of your fun work and getting the thing to do what you want, but you have to go through this process of writing to the firmware to actually get the chip to do what you want. So let's go through this a little bit more in detail. I know I said I just do a quick dirty version, but as I'm going through it, I feel like a little explanation is justified. Okay, this is the command that checks the chip. Now, I want to point something out immediately to you that is not very obvious in the code. If you look at the flash data, you can see every one of these bytes is a piece of your memory. Okay, this is quite a bit of data just by itself. Now, if you were to look at, you'll have to take my word that this is the default settings for the chip. You'll see that a lot of memory is just set to FFF, a bunch of it. And then you'll have a block that will have data in it, and then you'll have a bunch of blocks with no more data in it, you know. So you can see that if we were to write all this to the PIC, you can see it's quite a bit more data than what we have here, which is a total of like 16 blocks. All right, I'll show you later how many blocks it really is if you don't use this method. So What I do with this code, so you'll see it happen as you read the code, is that any address that is not basically specified in this array, in this block of memory, these are the addresses at each memory point where there's data in the BM71. If it does not find the address in this list of data, it will automatically assume that that 128-byte block is all Fs. It makes that assumption. So it can test memory that it doesn't find here. It will say, okay, well, I didn't find it in this list. Is it set to all FF, hexadecimal FF? If it is, good. If not, we've got a problem. Okay, so that's what's going on here. That's why there's only certain addresses here, is because if you look at this is the original flash, which this file is actually provided to us by Microchip in that BL3DK tool, okay? Be aware of that. So when you're going through the code and you're like, why does the code why does it only do some addresses and not others, and then just looks for FF all the time, okay? Now I have tested this code the way it is, and it does work by looking for the FFs. It saves you a lot of memory. Now, the other thing I really want to point out here, just because I thought it was very interesting and it's very useful, if you look at my memory, you see that I'm only using 16% or 651 bytes of my data memory. Data memory is like your flash. Okay, you have much less data memory than you do of program memory. You've got quite a bit of program memory, okay? You'll notice that I use the keyword constant on this data. That is because constant data cannot be changed. We can't edit any of this during runtime, but it will not store it in the limited flash memory on the microchip. Now, I don't know if it will let me do this, but let me try showing you an example. If I take out this constant keyword, let me see if it will let me program this. Qualifiers redeclared. Oh, yes, okay. Yeah, that's because I changed the constant on the actual data, so I've got to change the identifier. Let me see if it goes through now. What are you complaining about? Great time to have stuff not work on you. Let's see. Nope, that's not what I wanted. Well, damn. I was hoping to have this all work right out of the bat. I was actually working, this is actually, it is never called, can't find A2 words. Production has failed. Okay. This is kind of a weird error. I'm not sure exactly. See, I honestly believe this is giving me an error because it's just too much memory to use. It can't find the space. It doesn't have enough memory here to load all that. So let me see. Let's just confirm that. If I put const back in here, now let's see if it will, let me go through here. If it gives me that error. And it does not give me that error. So apparently all this data is so much that it overflows this this data memory. Okay, that's why it was giving me the error. So when you put this constant keyword in front of it, basically instead of storing it in your flash or the data on your chip, it stores it into the program memory. Now that means you cannot edit this during runtime. You cannot come in here and change any values. In this particular case, that's okay. Okay, so we're just copying this into the file, so it's not a big deal that we can't edit it. That's the purpose of the constant. If you take this out, it overloads your processor, or you can't use it. But it's literally only like 1% of your program data. As big as it is, it's only 1%. Now, that all being said, you can see if I had even more code here, then there definitely is no way it's going to fit into the data. So even with it being minimized, it's still too much to be stored into the flash memory, into the data. It's not, well, okay, it's semantics, but into the data memory here. Data memory is used for like variables, things that change. That's where that memory is used to. Okay. That all being said, I wanted to explain that to you. So you'll also notice that some of these other commands, any long arrays, I try and make them constants. This creates another problem where I can't edit these values directly. And you will find that some of the commands we need to specify like an address for that command. So for instance, when we go to read memory, we've got to say what address we want to read. Well, because the command is a constant to try and save room and clear out the buffer, because it's a constant, we have to load it into our buffer first. I have a write buffer here. So it has to first be put into the write buffer. It says the write buffer, it has the constant that can't be changed has to be loaded into the write buffer. Now the write buffer is a variable. It can be changed. So once it's loaded into the write buffer, then we can change the address of the command, and then we send it off. Okay? So be aware of that as you're looking through this code. That's what's going on here. Now, just for shits and giggles, let us see if I were to take out these constants. I know that that huge memory block over there is way too big to be uploaded here, to be uploaded to the data. But if I were to just do these bytes, let's see. So we're at 16%. Let's see what happens with just these few. You can see 16. It goes all the way up to 20, and I mean, you look at the size. 16 is that's 4%. That's almost 5% just for this little bit of code. So you can see how much memory these arrays take. So you can see its importance to use that constant where it stores it in the memory and not in the data. So you'll see me do a lot of things where I have to load it in into the buffer first, and then I manipulate it while it's in the buffer. Okay, that being said, let's go back to our main code. So we were going in here. Okay, so this is one of our first commands after the open. We do the checking. So what I'm doing here is I know the last address in the BM71 is this the last 128 bytes address is 1FF0. We can confirm this because not this file. Yeah, here. Okay. This isn't the one we're looking at, but you can see. Let's see. 1F00. This actually is not the right file. Okay, yeah, actually, yes. So 1F00 is the maximum value in here. So I say if it's less than or equal to 1F00, FF00, blah, blah, blah. Okay? This may be an error in my design. I probably need to stop it at 1F00. Instead of 1FF0, but I'll let you guys work on that. Okay, so this is just your basic for loop. It's starting at the 0 address. It's increasing by 128 bits. All the read and write commands write a total of 128 bits. I actually made code that used the 128-bit command to allow you to just write like 2 bytes. So it took me like a week. I figured it all out. I wrote it down. It all worked. Come to find out, when I really thought about it, you ended up having to do a way more reading and writing to check the code. The idea was that it would be more efficient on the memory. So I was thinking, well, if I can read and write 16 bits at a time instead of 128, well, then I can save space in my programming and not have to use as much. But you can see, since we have so much of this program memory, that whole section of code really is only like 2% of this. The rest of it is actually the program. That became less of an issue, and it was more of, I chose to go to 128 to check 128 bits at a time because everything was made for 128. It made the code simpler, and and it was faster ultimately. Okay, so the advantage to doing 16 bytes was the space savings. When I figured out that basically I wasn't taking up that much space using a constant modifier, I decided to go with 128 since there's almost negligible the size difference. I think it was like 1K or something size. Alright, getting off topic. Alright, so we cycle through the addresses, 128 addresses at a time, and this is, we're cycling through the BM71's memory. We're resetting the flag that determines whether the address was found in the data block, which is this one here. This is where we're looking for the address. Here, boop, 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 boop. Yeah, no, you're not gonna let me go back to it, are you? No, crap. Okay. I apologize. I'm sure you guys are like grinding your teeth right now because of how much I'm talking and going on. But alright, at least you guys are gonna get the full example. Alright. So we started the address 00. We go into a while loop. Basically, this while loop is checking if the if that memory address is found in the memory block. This is what I call the memory block. Something else to point out also is that this memory block is actually an array of structures. It's an array of flash 128T. That's why it's formatted this way. So when we access this type of, when we access this block, we will have the option to select the address at that index or the data at that index. Okay, you might want to look into structures a little bit more and using structures with an array because that process will be it'll be a little confusing to explain this next part if you don't understand that. Okay, let's go back to this. So going back to us checking here, so we're saying if we haven't reached the end of that data block over there and we have not found the address in the block, keep going until either we get to the end of the block or the address is found in the block. Okay, we immediately end if either of those happen. All right, so the while loop will index through that memory block. In this case, I think there's only like 16 indexes, so it's not like you're cycling through a ton for every memory address. So what you're doing, this is where I was talking about the structure, okay? This part looks like an array like you've seen every other array, okay? But this is probably what's going to throw you off. This is part of that, the fact that the data stored at that index can either be an address or a data based on that structure. So I can say, let me see if it'll do it here real quick. Block. Let's just say 1 for now. Now if I put period, see, it gives me the option to look at the address in that index or the data in that index, okay? So that is what that structure does for it. organizes that array so I can pull out just specific things, okay? So in this case, I'm looking at the first index, I'm looking at the address, and I'm seeing, does it match the current address we're on, yes or no? If it does match, then I set the flag, yes, the address is in the block. If I don't find it at the current index 0, if I don't find it at the first index, This will not execute, and so we will go to the next index, and we will keep doing this. We will go to index 1, check the address. Does it match the address? Yes or no? If it does, yes. If not, keep going. So we're going through that block looking for the address. Okay, and we're looking for the address here, this address here that we're cycling through. This is the address actually on the BM71 that we're looking through, okay? Now, if the address is found in that block, so this is the condition here. So if we do find the address, we use the BT compare memory command. If we don't find that address in our block, then we use compare empty memory. Now remember I was telling you that some of the memory is not included in there because it's all just Fs. So if we don't specifically include data, we only include data that's actually been modified in that block. So if it doesn't find that address, it assumes that that block of data or that address, the 128 bytes at that address must be empty. There's no data there, okay? So that's why it uses one command versus the other. Now what these commands do is compare memory, we send it the address that we're looking at, and we send it the data that that address should have, 128 bytes after that address. So what this will do is it will actually go, it will obviously clear the read buffer. We're going to read some data. It actually goes into the BM71 and reads the data at that address. Okay. Now this read 128 bytes, pretty self-explanatory. We clear the read and write buffer. What's going to do is, I was telling you about loading the command into the buffer first. So that's what this does, is it takes the read command, it loads it into the actual buffer that we're going to send to the BM71. Then while it's in the buffer, now that it's in the buffer and is able to be edited, and because we can't edit that command directly, we then update the address of the address that we actually want to read from. And that's what this does here. So if you go to this, I give an example of how it changes, how it sets that address. This BT send packet, you will see this everywhere. This is the core, the meat and bones of this code. What you first send it is you send it the buffer, the array that you want to send to the BM71. Okay. Now we have to tell it how many bytes we want to send inside of that buffer. In this case, you see, although I'm sending the write buffer, I'm really sending a read command, right? So the read command array, or the read transmit array, is actually only like 19 bytes, I think. So instead of taking this buffer is actually 147 bytes, and there's a reason for that, but we'll get to that later. So basically, we're telling this command we really only want to send 19 of the bytes in the write buffer. Then we tell it where, this code is something I'm still kind of in limbo working on. Really, this command should check the response and determine if the BM71 responded correctly, and it says how many bytes there should be a response for, but we don't, this doesn't actually do it that way. We'll get to that later. Okay, so really all that happens is that when you send this command, it populates the BT read buffer, this here, and oh yeah, okay, so it'll populate the BT read buffer. Now, the size that we're sending is very, very important. I want to point something out here. If the response from the unit is supposed to be like 147 bytes, in this particular case it would be, which is the full size of the read buffer. So I expect once we send this command that the BM71 is going to give a response That's going to be 147 bytes. It's going to fill up the read buffer. I have to give it exactly how many bytes I'm expecting back from the BM71. If I put too few bytes here, so let's say the command sends back 19 bytes, and I put 10 bytes here, this command will not properly populate the read buffer. Now, if I do the opposite and I put too many bytes there, let's say the response is supposed to be 20 bytes and I put 30, the code will get stuck. You will get stuck looking for the device to send you data back when there is no data to be received. So this is important. If you find that you're editing this code and you keep getting locked up and it's waiting for a response, chances are you've sent the wrong amount of bytes for the response. Okay, and this in the write command, what happens is there's a short. It's like a 19-byte command that we send to actually read 128 bytes from the BM71. But the BM71 actually responds with 147 bytes back, and the reason for the 147 is it's 128 plus the command, the response command of 19 bytes will be in front of the actual data, so you get 147. So there will be like a response like, hey, yeah, I got that command. Hey, here's all the 128 bytes that I'm going to send back to you, for a total of 147. So that's why you'll see that the buffers are 147. They're not some, nice round 150, is because 147 is the maximum response you're going to get when you're dealing with the dealing with reading and writing. Okay, so I lost my place here. Let me go back to this. So we had talked about comparing the memory, we talked about reading. Okay, so we were in the read command, so we load up the buffer we're going to send with the read command. We change it inside of the buffer, the address that we're going to read. This is the actual send command. So if you look here, this is where you guys will probably have to edit your code. So for my code, I have in my UART commands generated. This is automatically generated by the code configurator. Okay, these commands, I haven't edited any of these commands. Okay, the UART write, the process is basically it waits until it receives something, then it will return what it received. Okay, I take that back. I am wrong about that. This write issue, this isn't so much an issue, the write command. Okay, so you're just, whatever command you have to actually write an array to your UART command, your UART, that's the command you're going to change here. So let me see if it'll let me go back. Okay. That here, this is the code you're going to want to change. Everything else, this is to send 1 byte at a time, okay? Whatever command you have for your UART that you send 1 byte at a time, this is the command you're going to want to change. Now, once it sends that array, your buffer, it is going to wait for the response. So here is the read size for the response. This is generally where you're going to get stuck. Okay, and here's why. This is the second command. This is really the only other command that you're going to have to change for your specific PIC, is to read 1 character at a time from the UART. Now, your UART code should have already built into it a buffer, so you just have to call this command and it will keep collecting characters in order and everything. You shouldn't have to worry about any of that if you use that configurator. You just have to find whatever your command is called and make sure you're using that read command. Now, one thing I want to point out is this read command here. This is very important. My read command will force me to wait. It pauses until there's something to read. Okay? So this is something I'm not going to get too much into. This is something you guys probably have to figure out. So Basically, your read command for your UART will need to wait until something is actually sent. So if your code freezes up and you're in the debugging mode and you go to pause it and you see that your code pauses right here, it's because you've at some point sent. You at some point have sent. Let's see. Oh, dang, that was it. Okay. You at some point have sent the wrong amount of value for the command to respond with. So your UART is stuck and it's just sitting there waiting for more bytes, but the device isn't going to send you any more bytes. Okay, so be aware of that. That's mostly where your code's going to get stuck if you're sending stuff wrong. Oh boy, I gotta go through the main code here again. All right, so that's what we're doing here. So we were talking about going through the memory. We're looking if it is in that block. If it is, we compare the memory. Okay. We read. Okay. So we actually send the command to read back. Now, when we send this command, it will automatically populate our BT read buffer. This is where all of our data responds. Anytime we read from the UART, it's going to be from the BM71. It's going to be stored in this BT read buffer. So here is actually where I check to make sure that the make sure that the device responded with the correct command. So with the read command, specifically when you read from the BM71, the response from the BM71 is going to be 19 bytes. So see, I get the size of the read response. I want to know how big should the read response be. Let me see, it's 19 bytes total. This is what we expect. Okay. So yeah. Oh, jeez, I lost my place. Okay. Yes. So this is a for loop. What we're doing here is, I take it all back. We are not checking here. We are not checking. No. This is compare memory. Oh, jeez, I'm all over the place. Okay. Yes. So where is read memory? Compare memory. Read 128 bits. Okay. So we update the address. We load the read command into the buffer. We change the address of the read command. We actually send that command. We've talked about this command already. Here is where we check to make sure that the device responded correctly. So I made a mistake. I was looking at the wrong thing. I'm all over the place. Okay. So I think I'm going a little longer than I should here, but I'm going to try and hurry this up and keep it under an hour. Okay. So basically, so this is where we're checking the response. We're going through the first 19 bytes that the device responded with. That is in the read buffer. Again, because when you read bytes, the returned response will have the command that says, hey, I received the command, the first 19 bytes. We compare the first 19 bytes in the read buffer with the actual read response, which this read response here, we go byte by byte and say, all right, is byte 1 equal to the first byte in the read response? Yes or no? If it's yes, we do nothing and we continue. We keep doing that as long as the read buffer matches the read response for the first 19 bytes. We will not return a false. We will exit and return a true. However, if one of these bytes don't match, then we return a false saying, hey, something went wrong. We got a response from the BM71 that was not the response for a read command. Okay? So that's what this read bytes does. All right, so again, the main thing we're in here is the check configuration. We're going through all the addresses. Okay, sorry, I'm trying not to be too scatterbrained here. All right, so we were seeing if it's in the block. If it is in the block, we use this BT compare memory. We send the command to read from that address. Now, when this responds, it's going to respond with whether the return buffer had the response command or not. So this here automatically checks for the response command, as we saw. So for the response from the read command, so we don't have to check for that again. But now the response buffer, the BT read buffer, from 19 bytes and on, so after the size of the read response, all the way to the end of the buffer, that's why you get the size of the read buffer, we compare it with the data that we passed in from up here. From here. Okay? So if it is in the book, we compare the memory, we send the address, we read from that address 128 bytes. Now this is the data that we should get for that address in the memory block in here. So this is the data that we expect to receive back when we're at 0, 0, 0, 0, 0. So this is the data we're comparing inside of here. All right. I hope this is not too confusing. So this expected data is the array from that data block at address 0, 0, 0. So we're looking at the data that the BM71 actually sent back inside of the read buffer. We're starting 19 bytes because the size of the read response is 19 bytes. And it will end at index 18 because it's 0-based. So we actually start at 19 bytes at the index 19. I know it's a little confusing, but remember, indexes are 0-based, but the size is actually the size. So from 19 to the end of the read buffer is actually going to be the 128 bytes that the BM71 responded with that's in its memory. And we go byte by byte, comparing it to the data from the data from our memory block that we expect it to be. Okay, and then we return a false if it doesn't match. Return a true if it does match. Okay. Now, as we're doing that, as we're comparing the memory, if we get a false here, if we read something that if the data in the BM71 does not match the data that we expect at the memory address, we also, because the BT compare memory will return a false if the data doesn't match, we also return a false in the check config. So if something doesn't match, BT check config returns false. Okay? Now, as you can probably guess, if the address was not in the memory block, then we have a separate command, very similar process. So we go to this, it will read at that address specified. Here we actually check if the response was correct or not. I'm realizing just now that I don't have that check up here or down here that it should have, so that's something I need to fix. But now you guys are aware of it. Okay. Now, there is no data to pass into this, because remember, if it didn't find it in the data block over here, we know that the memory should be empty, because we're not including any data in this data block that is empty. That being said, we don't have to pass data into this to compare the return to. Instead, we do the same process. We send the read command. We start going through the 128 bytes But all we're doing is comparing all those bytes to 0xFF. All right, because again, what we're looking at here is we are looking at these blocks here that are all FFFF. So by doing this, we're saving a ton of memory. Just by assuming that if we didn't find this address in the data block, then it must all be FFFF. Okay, that's the reason for compare empty memory. That's versus compare memory. This we're actually comparing data that we expect inside of the memory, whereas this one we're expecting it all to just be Fs. Okay. So that's how this basically works. We go through and then we increment. So we do the 0 address. We increment by another 100. This is 80 in hex is actually a value of 128 in integer. So don't be confused. This is not 80 bytes. This is 128 bytes. It's just 80 in hex is 128. So we increment to the next address. So the next address will be 0080. If we look at our flash data, we see 0080. That is also in our block. So we will compare the memory. It won't be until we get to an address that is not found here that we will actually end up using the compare empty memory instead to check if the memory is empty. Okay. That, and also if it finds that the memory, if one of these bytes does not match 0FF, it means that it had data in it. Then it will return a false and say, hey, we got some kind of corruption data here. So if the memory does not match what we are expecting it to in the data block, or if the blank memory has data in it, this whole thing will return false. We'll know we have to reflash the memory. Okay, that's how this whole block works. Okay, so if both of these pass, we don't return a false, it returns a true, saying, hey, everything was good, we're all good to go. Okay, so now that we've explained that, back to the main command. Okay, that we just explained this whole command. Really, that's a majority of it. All there is this is very straightforward. We'll explain that in a second. And then we just have sending the EEPROM. Okay, so erase the flash memory. You may be asking yourself, why can't we just rewrite over the flash memory? Why do we have to erase it? It's kind of a scary thing to erase all the memory in the BM71 and then have to rewrite it. Here's the reason. This took me about a day to figure out. I was beating my head against the wall. It seemed like I was only able to write to the EEPROM one time. And that's technically not true. Okay, this goes into some kind of detail and gives some examples of what's going on. Essentially, in EEPROM memory, you can only change a 1 to a 0. Okay, that's it. You cannot change a 0 to a 1 in the EEPROM memory. If that sounds confusing, read that whole block. It goes into detail about it. So what happens is and it's hard to, if you don't understand that, it's really hard to troubleshoot what the hell's going on, because you'll write a byte to it and it will come out perfect. If you erase the memory, okay, let me take a step back. When you erase the memory, it sets every byte in the memory to 0FF. It sets the byte, all the bytes to 1. Everything's a 1. All right. So when you send your data, whatever needs to be a 0 will go from 1 to 0. And you'll have the data that you send the first time. Everything will work out perfect. Now, if you go to send another piece of data to the EEPROM, maybe the data you send, it needs to convert a 0 to a 1 because of the difference in the data. The EEPROM won't do it. It'll just stay a 0, even though it needs to be a 1. So now, you go to write a second value to that same byte that you've already written, and it doesn't match either the data you wrote the first time or what you're writing this time, because it creates a whole new value, because some of the bytes could flip, some couldn't. So if you don't understand what's going on, that's really maddening. You're like, I don't get it. It gives me the right value sometimes. Then I go to rewrite it. So, anyways, the whole point of that explaining this is that you have to erase the whole memory of the EEPROM before you can make any changes to it. That is a must. Okay. Otherwise, you get corrupt data, and it will screw everything up. Okay. So that is why every time we go to reflash the unit, we don't just try and change individual values. Now, here is what I want to talk about. So far, I've been showing you, you've got this block of data, which I'm still going to show you how to generate this. Don't worry. If you want to dynamically change values inside of the BM71 in here, you'll have two issues you'll have to work around. One is because you'll probably want this data as a constant, as we talked about, because of the memory issues. You will have to first load the block, the 128 bytes, into your buffer, and then you will have to make the individual commands that will flip the specific bytes you need. Now, I want to talk about this just for a quick second. Ignore this if you're not trying to change data dynamically. You're just going to use the code configurator that Microchip gives you, which I think is the simplest solution. Just ignore everything I'm about to say, because this is only for the people that want to change the data dynamically, okay? So just plug your ears for a second. Okay. In this tool they give you, this, I forget what I called it at the beginning of this video an hour ago, but this BLEDK tool which we will eventually get to, which allows you to easily edit the settings in the firmware here. In these files, you will find this table here called the BM70 BDLK UK perimeter table. If you open this up, you will find that it gives you specifically what bits in the memory at what address these bits are found at. I believe this is offset from 0, so this would be address 0088, and it would be only 1 byte that would be at that address. Not a bit, a byte, right? When they're talking about length, they're talking about the byte, not the bit. So you can change that bit to this value, and it will change the advertising preferred power level. This is what it does. Now, if you'll notice, some of this is in Japanese. Don't forget to scroll up, too. For whatever reason, when you first open this, it's all the way at the bottom of the table, and you just scroll down, you're like, what, that, like 5 commands? That's what they give you. But if you scroll all the way up, there's they give you a bunch of it. So this list right here, for those that want to change data dynamically, good luck. All the power to you. I don't disagree or anything, but you can see it's quite a bit of work here. Okay, so I want to. This is why I'm trying to say that. This is what I'm trying to get at, is that you can have this default table in here and still use this code. The only difference is what you'll do is when you load this into the buffers, you will use this table for the specified address to change the bytes, to change the settings, okay? So I don't have the code written out for this because I feel like this is very tedious, and I honestly don't think many people are going to want to do it this way. But if you are passionate and need to do it this way for some reason or another, this is how you can do it. You can use this table. You can, and you'll find that if you compare this table here, you'll see even when you change values inside of the code configurator, you should see that these empty blocks should still stay empty. You shouldn't find that like surprise, like all of a sudden we use this block, all of a sudden that by default is empty. You'll find that almost all those settings are going to change values where there's already data, where there's like 0, 0 or something. Now, I haven't confirmed that. I can't say definitively that's the case, but I think if you go through there, you're going to find that that's the case, that all these zeros is only where you're only going to write to data that actually has zeros. That being said, then this table is still valid for you because this table holds only the sections of code where there is actually data, so you can use the information found here to dynamically change at these specific addresses, how you want to change the values. Then you just send it over, you see. And then you'll have to figure out a way to dynamically check it, dynamically send it. I'll leave that up to you, but you can see that it'd be a very similar process. It's just a few extra steps that change this dynamically. Okay, so those that don't want to change data dynamically and just want to use the code configurator, you can unplug your ears now. So, going back to where we left off, so we were actually talking about erasing the flash memory. Here we go. It's a very straightforward, simple command. You have the erase transmit, erase response, response. Now, I don't know that this is necessarily needed, the delay 50 milliseconds, but I give it 50 milliseconds to go through and wipe everything clean before I continue. Okay. Now, I think in the example, actually, they even commented the delay out of the erase. I think they said that it wasn't needed or something, but I put it in there, what the hell. Alright, and then the last command to actually programming the flash memory is to actually send the new data. And this is actually not as complicated as you would think. It's not even as complicated as the read, okay? As the compare code. That's more complicated than this. Alright, now, when we write data, we need to know the size, because the size of this data block can technically change. We can either have 16, or we can have like 52 or 100 blocks that we need to write. Okay, technically, because that can change. We get the total size of all the data blocks, or the total size of the memory block. Okay. Now you're gonna run into a little problem. You're gonna find something interesting here. Normally, when you use size of on an array, it will return however many characters are in that block, or how many bytes are in that block. Okay, that's because it's a singular 1 byte per index. Okay, byte 1, byte 2, byte 3. With the memory block, because it is a structure, so again, let's just go back here. Okay, this whole thing is index 1. This is index 1. This whole thing, this is index 2. This whole thing, this is index 3. So each index is not only 1 byte. It is actually 128 bytes plus 2 bytes for the address. Okay, this address, each address is 16. It's 16 bits, not 8 bits. The data is 8 bits. The address is actually 16. So that means you have 128 8-bit words and 2 8-bit words, giving you 130 bytes for each index. Okay, does that make sense? Hopefully you're with me on this. That is why what we do is we get the total size of the memory block, all the bytes in the memory block. This will not return 16. This will return 16 times 130, whatever that is. It's been a long day. So it will return the value of 2080. So you'll be looking at this thing going, what the hell is going on? Okay, that is why we divide the total bytes by 130, because each index holds 130 bytes. So, using this formula and understanding that, we are able to get how many actual indexes are in that memory block. Okay, that's how we get the total number of indexes. And because this could technically change, we generate that number dynamically. Okay. So now we start going through the memory block. Okay. Now, here's something to understand. When we've already erased the memory block before we perform this operation, everything's already been set to 0xFF. So that means that all the empty memory that we're not dealing with, that doesn't have data, is already set to 0xFF. We don't have to do anything with that data. It's already been wiped out. All we have to do is write the new data, or the actual data that we want that's not erased. So all we have to do is go through the memory block over there, and we use this command to write the data. For each index, we pass first the address of that index in there, then we pass the data. It's pretty straightforward. And then we go into the write 128 bytes. You see that it's very similar to the read. We have a command called bt send 128 bytes. You have the address, and then you have the data. Now, when we did the read 128 bytes, we would send a 19-bit command or 19-byte command. We would then receive 19 bytes from the BM71 plus the 128 bytes that it read. When we write to the BM71, we do the opposite. So we put in, and let me just go to this. We clear the buffers out, the read and the write, before we transmit. So we load the write command in to the buffer, right? This is the copying process since we were using constants. We change the address that we want to write to here, all right? This stuff just talks about what we've already talked about with the EEPROM. or no, this is... yeah, it does refer to... whatever, I'm getting off topic. You can read it. Screw it. All right. Now, before we can send the command to write to the BM71, we have to add the data that we want to write after the write command in the buffer. So when you watch this populate in debugging mode, you'll see that there will be 19 bytes that are of the write command, and then you will see 128 bytes after that that actually contains the data that we want to write. So the write buffer also needs to be 147 bytes, 19 plus the 128. So we send that full 147 bytes to the BM71. This time the BM71's only going to respond with a basic read command. It's only going to respond to the response for the write command, which is 19 bytes. It says, hey, yeah, I got the data, I wrote it, we're all good. Okay, and so here I just check to make sure that it did in fact give me the right response for the write command. If it doesn't, I return a false saying, hey, something went wrong, we tried to write the data, it didn't work. Otherwise, we return true. Oh, no, okay. Send config, okay. So we're essentially just writing this data to the memory, and we're cycling through the block. Now, what you're going to notice is that we send the data to the block, but after we send the data, we also we go back and we read that data again. So we send the 128 bytes to configure the data, then we read that same address back, 128 bytes, and we down here, we should now have um, we're comparing the data here that we passed in originally, or that's the data that we're comparing it to. We're comparing it to the read buffer to make sure that that we actually wrote that data. So we're reading again. After we write it, we read it again and make sure it matches the data, that there's no corruption. We return a false, if there was corruption, return true if everything passed. All right? So even though it says 128 bytes write to flash, it's not only writing each 128 bytes, but it's also reading back 128 bytes and comparing it to confirm that everything got written. Okay? So let's go back to our file, and I realize this is taking a lot longer, and I still haven't even showed you the process. I'm just explaining the dang code. Okay, so we understand this is where we're just comparing the block of data to the code. We understand now that we have to completely erase the data. This is what we were just looking at, where we configure the data. Now, even though we write to the unit and then read to compare each 128 bytes, we still do a final full compare to make sure that, the addresses didn't get shifted or some weird goofy thing didn't happen. So we do a full read, a full compare again to make sure everything's good. And if everything's good, I just turn on a LED. And then we've already talked about ending it and going into app mode. Now, assuming that all this goes well, hopefully I've explained the code enough that you should have a good idea of what's going on, even though it's taken like a whole hour. I apologize. This is the code that I just recently started working on, which is to get the local info. So this command will not work until you actually configure the device the right way. So if you want to know how to configure that device, if you go back to the microchip developer page, if you go to the gap preheasable demo, this was actually the demo I was following to set it up so that you are not in auto pattern, you are in manual pattern. Okay. When you are in manual pattern, you are taking the device out of that UART communication protocol. You can then send the commands like this one here, read local info, which basically uses the same method of loading the buffer from the actual command. So here's the actual command. So then it loads it into the buffer. Now, in this case, with these types of commands, we have to add a checksum. Now, I'm just going to briefly go over this. This is confusing as all shit. So basically, a checksum basically is a number at the end of every command to just say, hey, if you do this math on this command I just sent you, you should get this number. And basically that's a way of to check that the command sent was actually correct and that there was no corruption in the command. You can look into checksums. I'm sure there's better explanations. So to generate the checksum, because there's very little data on this, again, for your AA codes, your opticode, whatever the hell I call it again. Once you're in application mode, and you've configured it to be in application mode, going through this tutorial and doing that, you actually take it out of auto mode. And I'll put the link to this tutorial in the description below. Once you get out of test mode and you go into application, you'll set to generate the checksum, you'll set the checksum to FF to start. You'll then subtract the value of each character in the total command. So it first is subtracting and in fact I should point this out, you do not include the very first byte. You do not include 0xAA when you do the checksum. It's only the bytes after, and then you do not include the very last byte, which is where your checksum is going to be. This will end up being the checksum. So you're basically just subtracting the values in between there. So in this case, it'll first start with FF. It'll subtract 0. 0 from FF is just FF. It'll then subtract 1 from FF, which will be FE. It will then subtract another 1 from FE. She'll make it FD total, okay? Now, once you do that, if for whatever reason you have to add this 0, 1 to it at the end of doing this process, and then what this does is after the checksum has been calculated, we've gone through and subtracted all the characters, we've added our 1 to it, then we put it at the end of our command here. Now it does it in the buffer, it's not doing it directly here, but we have to save a space for it in the actual command itself. But that's why it has size -1, is it will actually populate it here. So then we add it to the end of our command. So that's what add checksum does. This is the pin I keep telling you guys about that I recently found out, the pulse wake up. You'll notice that when you go here it says RTS set low. I've already explained this is due to my screw up on the board. It's not really supposed to be RTS low, it's supposed to be wake up low because I'm not using an RTS pin. I just threw it to RTS. I think you get the idea. Then we can use the same command that we use for the packets and the erase and the other buffers. We use in the flash memory, we can use the same command to send that buffer out to the BM71 and see what we get back. And so if you have it configured right using this tutorial, it says you should get something like this command back here, where you get AA00E8001, blah, 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 blah. And after running this code, I've actually gotten that back. Don't worry about this. I just threw 100 in there because I haven't quite, again, this is in progress. I haven't quite figured out how I'm going to deal with the response bytes and all that. So that's where I'm at with this. So I think I'm actually going to end this video here, and I'll just label this as explaining the code, since that's pretty much exactly what I did. And I will actually make another video of just doing the quick process, so I apologize. At the beginning of this, I said, oh, I'm just going to show you quickly how to do this, all blah, blah, blah. And I ended up doing an hour and 30 minutes on how the code worked. So I'm done for now. Hopefully it's a little easier when someone explains how the code works than trying to figure it out yourself, even though it's commented to hell, so that should help too. Alright.